Προχωρώντας, η κυρία Όλγα Αλεξοπούλου θα μας πει κάτι πολύ επίκαιρο και έχει να κάνει με τις τελευταίες εξελίξεις που έχουν γίνει και στο τομέα της χημείας. Οπότε, the floor is yours.
Thank you. Hi. I'm here to talk to you about quantum pigments. Quantum pigments are made out of some very small particles that are capable of bringing a very big change in the world of colors by creating paints, dyes, and coatings that harness the incredible optical qualities of quantum dots. Now, most of you know that this year the Nobel Prize of Chemistry went to quantum dots. Our company is the only company in the world that specializes in quantum pigments. And we have the intellectual property portfolio for quantum pigments, which is why a well-known businessman told us that we need to set aside $10 million for lawyers' fees because everyone and their mother will come after our IP. So how did we get here? The story starts about 4 decades ago, when 2 of these scientists were working on identifying and inventing what we now know as quantum dots. Alexei Ekimov was working behind the Iron Curtain, so his work wasn't made public for a bit of time. At the same time, Louis Bruce was working in America. Bruce had 2 star students. One of them was Mungi Bawendi, pictured above, and the other one, my mentor, Paul Alivizatos, seen here accepting the National Medal of Science from President Obama. When I first contacted Paul, he was the director of the prestigious Berkeley Lab, an internationally recognized authority in quantum dots. I thought it was mad that quantum dots weren't already used in art. You see, as a painter, I was always fascinated by the history of pigments, stretching at least 64,000 years ago, and I have traveled to many remote places to find unique and historical pigments. So I emailed Paul with an idea to create the first quantum pigment. Luckily, he accepted my project, and in 2018, with a small team of scientists, the first crude formulation of quantum blue became a reality. Then Paul connected me to Jason Hartlove, who was the then president and CEO of Nanosys, the Silicon Valley company Paul had founded a few years earlier. He connected me in order to explore the commercial application of quantum blue. Most people know Jason Hartlove as the inventor of the billion-selling optical mouse, but actually he's responsible for the meteoric rise of Nanosys, which is now the best company in the world for quantum dots. So Jason and I decided to start a company dedicated solely to quantum dots in making quantum pigments. Quantum Light, as the company is called, aims to revolutionize the world of colors by creating pigments and dyes that harness the unique properties of quantum dots. So, what exactly are these quantum pigments? Quantum pigments are composed of nanocrystals called quantum dots. The yellow sphere is not the sun, but a tennis ball for comparison. You see, quantum dots are 60 million times smaller than a tennis ball, and just a bit bigger than a water molecule, typically between 2 and 8 nanometers in diameter. Quantum dots are small particles of crystalline semiconductors, typically core cell structures that exhibit a property known as quantum confinement. The size of a quantum dot determines its wavelength, and thus color output. As you can see from the diagram, the smaller the dot, the more intense and hence blue light is emitted. The bigger the dot, the redder the light that is emitted. Because of all this, quantum pigments will have phenomenal optical qualities, including being illuminant independent, being significantly brighter than conventional pigments. This, as I will explain in the next slide, is because of quantum confinement. Being able to emit light at any specific wavelength in the visible spectrum. Quantum dots can be engineered to emit at any chosen nanometer of the spectrum of light. This actually goes for the visible, but also invisible for humans, part of the spectrum of light. And finally, For the first time, we are manipulating light to create pigments never seen before. To quote Jason Hartlove, we will be painting with light. This very simple diagram is actually the most important one in my presentation, because it actually explains what happens when we utilize quantum confinement in pigments. Conventional red pigments absorb light and reflect only the red part of the spectrum. Quantum pigments absorb and then emit the whole spectrum, but convert it into the specific chosen red color, down to the nanometer. This makes them not only significantly brighter, but also it means that the color does not change depending on the environment's illuminant. What does that mean in practice? Imagine that you have a car painted blue with a conventional paint, and at night you park it at an underground parking lot. Usually these parking lots have orange lights, which means that when you will be looking for your blue car, it will appear green. Whereas if it was painted with quantum blue, it would always appear blue, because it would always be emitting at the chosen wavelength, and you wouldn't lose your car. All these unique optical qualities make quantum pigments the next chapter in the history of pigments, a future with brighter, consistent color. We created this setup of photos to explain in practical terms what we mean by brighter and consistent color. Needless to say, neither this projector nor the screen can portray the actual intensity of the color of quantum pigments, but it will have to do for now. In the three photos, you see a few Coca-Cola cans and a vial of quantum red in three different lighting conditions: daylight indoors, reflected daylight indoors, and shade indoors. Reflected light of conventional pigments changes color depending on spectrum of illuminant, whereas quantum dot paint always emits the same color. As you can notice from the far right photo, in a shaded indoor environment, the vial of quantum red looks significantly brighter, which means that if a product is painted with quantum red, it will appear very bright even in a shaded corner of a shop. This opens up a whole new way to market products. So this brings us to the question, where can quantum pigments be used? And the answer is pretty much everywhere. Art, architecture, apparel, automotive. In fact, one of our scientists said, if we ever created hair dye with quantum pigments, it would look like CGI characters walking the streets. What about environmental facts? As you know, the production of an average kilo of conventional pigment produces approximately 10 kilos of waste, which is mostly discarded in countries like India and China. And if we think about the textile industry, well, it uses 1.3 trillion gallons of water to dye garments, enough to fill 2 million Olympic-sized swimming pools. Most of this water, loaded with harmful chemicals and dyes, flows untreated to rivers and streams. Whereas our quantum dots are produced in a net zero factory where the little water that is used is continuously recycled and reused on the premises. Products in development. When we think of quantum pigments, we think of the colors we already know, but brighter and consistent. However, there is more. For example, our team is developing quantum black, a super black with a red glow. This new super black is achieved by especially formulated quantum dots that take light and emit it back in the non-visible part of the spectrum and only leave a tail of emission in the red. This creates a very intense black with a mysterious red glow. There are loads of pigments just like that that are waiting to be discovered. Pigments that create a play between the visible, the invisible, and with tail ends in all sorts of colors. And we're only just beginning. Thank you.